I thought it'd be useful also just to talk about some kind of broader work that we've been doing, mostly because I think there's some of it has little bits of crossover with other people's work, and it's often just good to get a general sense of things that are going on. And I've given it this slightly grandiose title of Climatic Changes Experienced by Life on Earth. Um, but what I really mean by that is that when we traditionally have done any kind of climate change impacts analysis, what we're essentially doing is using data that has been collected by a sort of series of weather stations that are dotted all over the world. And they have little thermometers in a white box, typically, that looks like this. They're kind of shielded from direct sunlight. They're always in a kind of open area. They're always sort of about 1.5, 2 meters above ground, and it's collected in a very standardized way. And typically, even when you use gridded data sets of future climate change that are essentially meant to represent that kind of temperature that you measure in the shade at a standard height. Now, if you're a little creepy crawly crawling around in the grass, or indeed if you're any other living organism, you generally don't live in a white box. You generally live in somewhere that's exposed to wind. You generally live in somewhere that is exposed to sunshine. And that temperature can actually be incredibly different from that temperature that you measure at a weather station. And so if you're therefore sort of thinking about how does climate change affect life on Earth, we maybe need to start thinking not about the sort of climate projections that you measure from a weather station, but you actually might need to start thinking about how climate, how a little organism that's actually living in the wild experiences the climate. And so really this has been my sort of mission, I guess my kind of research goal for a few years now, is to try and really get to grips with that. And what we've done actually is develop a whole series of R packages that I'm just going to give a bit of a headline overview of, that make this fairly straightforward. They're essentially physics-based models that really get to grips with how organisms experience life, climate change. So what we've done is we've developed a whole sort of series of packages, and I'm going to give you a bit of an overview of the different packages. We've firstly got this what I call micropoint package. If you are interested in, say, the temperature experienced by a tree or an insect 5 centimeters above the ground, if you're an insect or in a tree, and you're interested in it at a certain location, and you know that location, and you know some general characteristics about the landscape around that location, you can use this micropoint package, and it will do a whole bunch of modeling, and it will actually give you things like the leaf temperature of a tree. It'll give you the air temperature surrounding the organism, and then there's some sort of bolt-on functions. You can actually calculate the body temperature of an ectotherm or heat stresses of an endotherm. We get this sort of microgrid set of packages, which comprises two packages. One is a microclimate modeling package that really gives you insights into how organisms experience climate if they're exposed to sunshine and wind. And the other one gives you, it's essentially a climate downscaling package. So it essentially takes the kind of weather measurements that would be taken by a weather station, but actually just downscales that to higher resolution. And those ones sort of operate at landscape scale. So there's a whole bunch of processes built into them that allow you to do the landscape scale stuff. But also because often you want to do things at high resolution over quite big areas, there's a few computational tricks we use to speed things up slightly at the cost of the kind of accuracy of the outputs that you get. What it, so one thing we found when we've been working with sort of microclimate modeling and having people sort of use these packages is that actually the biggest challenge that comes with them is trying to wrangle the data that essentially feed into the packages. So what we're just working on at the moment is another package that essentially uses kind of API download of various data sets and essentially does that in a very user-friendly way. So you've just got a headline sort of series of R functions that enable you to source all sorts of data that are useful for this kind of thing. And then to sort of make it computationally fast, though it's got an R front end, it links to a C++ library. And then you generally find that most of the API download stuff's a bit better in Python, but you can link between R and Python quite easily. So this is essentially, I'm just going to give you a little bit of a kind of overview of the kind of stuff, outputs you get from the packages. And this is really the one that we developed actually under our trees, although we had sort of previous versions of this that weren't quite as good. And so I essentially bundled a load of previous code that we did together with Jonathan. We bundled a whole load of code together. And essentially, the way it is sort of its primary use is that if you say interested in climate at field parcel scale as opposed to at 1 kilometer grid level, you can just downscale it to that level, and it takes into account some various processes like elevation. It will generally sort of capture quite well the fact that temperatures tend to be a lot more stable if you're near a water body near the coast. And then it also sort of captures some of the more complex processes that you get in more mountainous regions where you sometimes under the right climatic conditions get cold air drainage effects, things like that. But then there's also a few other little tricks that we put into the package to help with things we're very interested in at trees and modeling things into the future. Now, typically, if you get a climate data set for the future, it typically particularly if you're using UKCB simulations of future weather, you find that actually, if you just modeled it using the raw simulations, what you think is a climate change effect is actually mostly, or to some extent at least, as a kind of modeling artifact effect. There's a whole series of biases in the future data. So particularly things like the diurnal temperature ranges tend to be underestimated. But what they've also done is essentially run the models backwards for historic periods. And so you've got a historic model run, and you obviously can't get hold of real historic climate data. You can put those two things together and you can do a bias correction. And this essentially contains a whole set of tools for doing bias correction. And then the other sort of final thing is we just put a few things that's quite often quite handy to be able to temporally downscale climate as well as spatially downscale it. So there's a few sort of things that allow you to simulate realistic daily cycles of solar radiation, for example, or reproduce kind of realistic temperature cycles. And having sort of produced this package, you can then, so we're in the process of sort of fully coupling that up with the microclimate model, which I'll talk about. And sort of having done that, you can sort of start playing around. Everyone likes a bit of a map, and I was just having a bit of fun with it. Sort of stemmed actually from the fact that when I moved house up the road, I suspected I moved just by moving up the hill from the subtropics to the temperate region. And we wanted to just wanted to check this. Indeed, if you define sort of subtropical as having an average temperature of 10 degrees plus over 8 months a year, you can see that actually you can start picking out precisely where in the sort of region is subtropical and where's temperate. This is essentially just over a number of years, the fraction of years in which you get a subtropical climate. But you can sort of really sort of start to see the merits of doing things at slightly higher resolution if you zoom in of a kind of more complex area like the Scillies here. And you get a sort of comparison of what you get out of the package if you just look at the relative to the raw 1 kilometer gridded data you get from the Met Office. I don't know, the Met Office, they've sort of forgotten about a few of the outer islands on the Scillies, but actually, the package handles that kind of thing quite well. So this is essentially a climate downscaling package. So then we've got this kind of micro point package, which is, say you're interested in what the temperature of the body temperature of a pest species might be if it was actually in a crop somewhere and therefore experiencing a very different climate from kind of measurement by a weather station. So yeah, essentially this just allows you to do a whole kind of a bunch of calculations to actually get the body temperature estimate or the microenvironment it's surrounded by. It's really quick. You can get a whole sort of set of different climate parameters, and then there's kind of an add-on that actually allows you to do the body temperature of the organism, and it's also got a sort of simple snow model built into it as well. And it's really quite simple to run it once you've got your input parameters, just a function, and then you just get a kind of time series plot like this quite easily. This is just sort of showing you the difference between below canopy and a kind of standard weather station measurement. But everyone likes a map. Points are useful in some instances, so we've just sort of taken this a little bit step forward. And I guess the kind of key distinction is, to some extent, all you're doing is running the same code on each pixel individually. But there's also some, actually, we delved quite deeply into the physics of the model to kind of simplify it a bit. And we found there were lots of things we could do to this, slightly sacrificed on the accuracy, but did make it a lot quicker. And that sort of starts meaning that you can get really high resolution maps of how climate is experienced by organisms across real landscapes. And again, it's sort of moderately sort of quick to run. You run the point model, which does some of the background calculations that then feeds into the grid model. But ultimately, you can get the sort of maps that look like this. So you can run it in kind of hourly time steps, or you can sort of select subsets of days in the year, the kind of days you'd expect to be hottest or coldest. And, you start getting sort of real sort of visualizations of what the climate actually looks like. And you can see it's really quite variable at that kind of scale. And if you're thinking about sort of 2-degree temperature rises, kind of matters the fact that you've got a much, much bigger variation than that across the landscape. So then finally, there is this kind of microclimate data package, which I've been working on very recently. And this is just a kind of a collection of fairly useful functions for downloading various useful data sets, particularly with this kind of microclimate modeling and climate modeling in mind. But then I've also been thinking about the fact that having a kind of user-friendly library of functions that you can download data sets easily has applications beyond that. And at least with R, it's a little bit of a gap. There doesn't seem to be a package that does that at the moment very well. But yeah, these are the kind of data sets it downloads at the moment. There's just a list of them there. And I mean, just to give you some kind of examples of the kind of outputs you get, if you want to download additional elevation data, you can do that really easily. It's very, very quick to do that, even for quite large areas. This is just Alpe d'Huez. I don't know if you watched the Tour de France. It's one of the killer climbs in the Tour de France, but you literally can just sort of give it a template raster or lat long, and it'll just pull off the data off the Amazon web server. So the other thing is that actually for a lot of microclimate applications, knowing things like the vegetation height is incredibly useful. And there is this really good global data set that's high resolution, that just sits there on Google Earth Engine, and we've just developed some functions that, again, it just pulls that data off and it downloads it into your Google Drive, and then you can use it however you want. But it actually, if you zoom on the sort of areas, this is the Lizard Peninsula down in just that way. Actually, you can see it from here almost. And, actually, because I sort of know this area quite well, the data's realistic in terms of what it tells you. So I noticed that people were asking me fairly recently about sort of automated download of the leaf area index. That is in this package. I've made some progress actually on that just in the last week. It's what I've been working on quite a lot. And this essentially, it just downloads data from the Wekio website, and you've got 10-meter resolution LAI data, at least for parts of Europe, available for that. It's also got a bunch of, you can also get data from other sources, but at coarser resolution. And then it's just got some sort of functions built into it for dealing with cloud cover and things like that. Because when you pull the raw data off, it tends to have little gaps in it and holes in it with this cloud cover.
What's the time sample one?
It's what you find is that in theory it's every 5 days or thereabouts every time they do the satellite pass, but almost all your data is cloud filled about 3/4 of the time. So actually, what I end up the function what you do is you pull off the data for a kind of finite time period, and then you get about sort of loads and loads of data files, and then it just crunches through them, and then it kind of mosaics them all together and kicks out the stuff that's not good, because there's actually a quality flag that comes with the raw data. And actually, the annoying thing is, even through that automated download, you get a bunch of corrupted files, so you have to scan through them, check for corruptions. But that's partly what the package does. But it's pretty good. I mean, you'll easily get monthly data off this, probably weekly. I mean, certainly for your crop stuff, it would work. The only thing is that it is a kind of swath across Britain. I think they're expanding the coverage, but at the moment you don't get coverage for the whole of Britain. And then how am I doing for time? I can.
Very well, 17 minutes.
Okay, just this is a bit of a kind of potted history. Some of it's just sort of fun of just some kind of stuff we found out about the models that's a bit interesting. Try to convince people that sometimes we do need to think about climate in a slightly different way. But if I'm running short of time, Dan, just tell me to hurry up. I can skip over a bit. So a few years ago, we thought, okay, we'll apply these models. This was an earlier iteration of a mesoclim model, actually. We thought, okay, we'll look at how sort of variable climate changes across lizards, being my sort of long-term study area for ages. I do tend to do most of the stuff there. It turns out it's actually surprisingly variable. You sort of think about sort of variation across Britain, but actually just over an area like the lizard, you can see there's some real patterns in how quickly places are warming. And that's actually largely driven by sort of changes in the weather patterns and things like that, having variable, locally heterogeneous effects. Annoyingly, though, doesn't tend to be a sort of fixed pattern. It tends to vary from year to year and across decades. And so, the places that are warming slowest over, say, a period of 10 years, you take the next decade and it's completely different 10 places that are warming slowest. So it's quite complicated. This is worth thinking about if you're thinking about pests. It's kind of fairly well known anyway, but if a little insect is basking out in the sun, its body temperature can easily get 20 degrees hotter than the kind of ambient air temperature measured by a weather station. And again, you think about 2-4 degrees climate change. If we're not really capturing that kind of thing, it's you're going a bit wrong, right? And again, really that sort of offset, it can be really quite variable. Obviously, on a sunny day, it's going to be much hotter, the difference between the air temperature and the body temperature. And so if you've got changes in cloud cover, which we know are happening alongside climate change, the way that organisms respond is going to be quite different to how you'd predict it with macroclimate. This was done by one of my postdocs, Ali, and one of my old PhD students is now in postdoc. He took the model a bit further. Butterflies, they have quite complex wings. They sort of absorb sunlight or solar radiation in quite complex ways. They sometimes even act like a photovoltaic concentrator. They hold the wings like that, but sunlight sort of bounces down onto the thorax. But he wrote a little model that kind of calculated all of that we could apply in the real world, and we found that when a butterfly flaps its wings, it basically changes its body temperature by way more than climate change over the next 100 years. Then we thought, well, okay, one of the sort of common conceptions is that as the climate warms, you've got a whole tranche of species that would typically have to shift their ranges towards the poles to track that climate change. And that's been a mantra in conservation for about sort of 20, 30 years at least. People have said, okay, we need to connect all our nature reserves up, we need to improve habitat connectivity. And I said, okay, well, what happens if we take the models that predict that and we actually run them with fine resolution data instead? It turns out they don't need to move very far at all. Instead of actually being sort of projected range shifts of several kilometers per decade, it was several 100 meters per decade at most, sometimes even less. But it's actually quite a complex pattern, and it has to do a lot with how you're estimating the thermal niche of species using macro and microclimate data. But then actually we thought, well, we could apply this to crop models. So we started sort of applying these kind of techniques to a fairly simple crop model. We've worked with Warfuster before, but this was a really simple crop model called EcoCrop. And we just projected globally where by 2080 and by 2040, you'd expect sort of crops to end up based purely on climate suitability, nothing about whether or not actually people would grow them there. And it turns out that actually a lot of the world's last remaining wilderness areas being quite a high latitudes. Basically, the reason they're wilderness is people haven't been able to farm there largely, so there's less people. But it turns out quite a lot of them are under threat, and actually they're really disproportionately under threat relative to other parts of the world that aren't wilderness. Can also lead to some sort of surprises. This was some work Jonathan actually did a few years ago where we were trying to sort of get to grips with how advances in phenology interact with temperature into the future. So if you've got a warming temperature, typically things happen earlier in the year. And so basically you've got this kind of opposing effects. You've got warming temperatures which might reduce something like frost risk, but then it's also happening earlier in the year, so you might actually increase. And at least for certain varieties of grape, we found that warming temperatures could actually, because of that phenological advancement, could increase their exposure to frost risk somewhat counterintuitively. Got an MSc student to do that with adders, and it turns out you get a very similar thing actually, although again it's really quite complex and spatially variable. Some places you had reduced frost risk, some places you had increased frost risk. Then we thought, well, okay, one of the things about a lot of species is that they live under forest canopies, and forest canopies are really the climate conditions are really quite different from the measurements that you take in these open areas by a weather station. We thought, okay, what we'll do is we'll model climate underneath the world's tropical forest canopies. Historically, people think about the tropics being places that are quite slow in terms of climate change relative to places like the Arctic. But what we found is because conditions across the year below canopy, and also because of the buffering effect of the canopy, you get a lot less sort of normal variance in the climate over shorter time periods. When you do get climate change, that actually transitions you into a completely novel climate regime. And it turns out that somewhere around sort of 2/3 of the world's tropical forests below canopy, that's kind of actually already has transitioned to a completely novel climate regime, which perhaps sort of explains some of the kind of species extinctions that it already started to occur in many regions of the tropics, for reasons that can only really sensibly be attributed to climate. And then I showed you the map earlier where It essentially modelled whether it was subtropical now, but then because we've got the tools to bias correct, you can also project that to the future. Turns out it's going to become increasingly subtropical in northern parts of Devon as well as down here. Although when we sort of started this work, I did a kind of earlier iteration a few years ago. It was picked up by a few papers, but you discover that some of the Daily Mail readers are your harshest critics, and not everyone believes the work that you produce. But yeah, anyway, I'd finish up that slightly trivial note, and hopefully some time for questions if anybody's got any.